All right, so yesterday I was talking about the projective case, using large margin for the projective case, so we extend the previous lecture to the non-projective case. But of course, because we are using non-projective dependency parsing, for the inference we use spanning tree algorithms. And so we are explaining, I'm going to explain this article by MacDonald again, but it is for spanning tree and it is non-projective. And in the non-projective case, as I said, they cross each other like this, here and like here and like here, because in Czech it happens a lot. They cross each other. Most of the time they are non-projective. The rich languages like German, Dutch, and Czech are non-projective. And non-projective cases, trees are more preferable in some cases. So my previous lecture was for projective case. Now we want to extend it to the non-projective case. So as usual, we create the scores for each edge. We learn the weights and FR features. Again, we do feature engineering to obtain them. And so the score of a dependency tree for a sentence is the sum of all edges, score of all edges. And the minimum spanning tree, we want to find the maximum spanning tree because the maximum score of a tree, we need that. So of course, any algorithm for minimum spanning trees can be also extended to maximum, no problem, but negation, we know that. And we use a CLE algorithm for finding maximum spanning tree. And it uses this contraction, just like the work of Karger in randomized algorithm. It's about contraction. So let me walk you through that. So you connect words to each other, and the first step is to find for each word, for example, saw, for each word, the highest scoring incoming edge. For example, 20 is the highest scoring in comparison to 10. 20, so we collect for each edge the highest scoring incoming edge. If the result were a tree, so the first step is to find for each word the highest scoring incoming edge. If the resulting were a tree, it would have to be the maximum spanning tree. So now it's not a tree. However, in this case, we have a cycle. You see 20, 30 is a cycle, so it's not a tree. So it's not, the algorithm is not ended here. In that case, we have a cycle, so we will contract it. So we will contract it to a single node. So John saw is contracted. This one is here, John saw is contracted to single node. So this is just a single node. We have contracted because it's a loop, okay? We contract all the loops. And the new vertex represents the contraction of the vertices John and saw. And now the edge from WJS to Mary is 30. Since it is the highest scoring edge from any vertex, the edge from root is set to 40. And root is here. So root is 40. Since they were representing the score of the best spanning tree, The same leads to from Mary to WJS. So the fundamental, and then contract. So the fundamental property of CLE is that maximum spanning tree can be transferred into maximum spanning tree in the original graph. Thus, we recursively call the algorithm on this graph. And we need to keep track of real endpoints of edges into and out of WJS for reconstruction. So, a possible concern with searching the entire space of spanning trees is that we have not used any syntactic constraints to guide the search. And many languages that allow non-projectivity, like Czech language, are still primarily projective. By searching all possible non-projective trees, we run the risk of finding extremely bad trees. So this is a special case of Mira that we put k equal to 1. So in Mira, we don't minimize W, but we minimize the changes of your weights in this iterative algorithm. And as you remember from the previous lecture, if the loss is high, the difference from the goal score and the predicted score should be high. And if it is low, this difference should be low. So it keeps that structure. And for single best Mira, it means instead of k best, we use just k equal to 1. For factored Mira, this is another possible way. We just use subject to SLJ, KJ. So L to J, K to J. The score from L to J minus the score from K to J should be greater than 1. This states that the weight of the correct incoming edge to the word and the weight of other incoming must be separated by a margin of 1. And now they have compared, in this paper, they have compared these 5 systems. The original McDonald 2005, but they use it for k equal to 1, and also factored that I just said. This one is factored Mira. So they compared and noticed that, and of course here complete measures the number of sentences in which the resulting tree was completely correct. You see, for Czech, the result is 84, and for the complete is 32. For different systems, as I said, we have 5 systems, 1, 2, 3, 4, 5 systems.